My name's Tim. I'm a Senior Principal Engineer at Aurora, and welcome to DAT441, where we're going to talk about Amazon Aurora and its innovations this year. So we've given this talk every year for quite a few years now, but this year it's going to be a little bit different for two reasons. The first one is, if you've seen one of these talks before, I'm not the normal guy, I'm not Grant. But also, secondly, it's because Aurora turned 10 this year. So if you're not up to speed with that, then that means, yes, thank you, congratulations, Aurora. That cake was delicious, even from the other side of the world. So what it means is that we did this live streaming event and we went back, so you could watch this live stream, still at the QR code if you'd like. You can hear from some people who we still have working for us for those 10 years and see a bunch of cool demos and stuff. So I really encourage you to check out that live stream. But if you haven't seen this talk before, I just want to orient ourselves a little bit. So what is Amazon Aurora? So Aurora is a cloud-native relational database that combines the speed and availability of high-end commercial databases with the simplicity and cost-effectiveness of open source. So it's fully managed, fully compatible with MySQL and Postgres, respectively. It's got a whole bunch of tools that allows us to plug into serverless, machine learning applications. Because it's compatible, it means that your applications don't need to change in order to use Aurora. And it means that all your extensions work for Postgres and things like that as well. So the most recent addition to the Aurora family has been this third engine called Aurora DSQL, Distributed SQL. So this talk's not going to focus deeply on DSQL. We will talk about it a little bit towards the end. So if you're interested in DSQL, I'll put some other talks up at the end which you'll be should be going to have a look at as well. Okay, so I'm an engineer, right? So this is a technical talk, so I need to get a little bit technical. We'll talk about the architecture of Aurora first, because this underpins a whole bunch of what we're going to talk about today, and I think it's a bit cool. So if you're not interested, too bad, you've got to listen to me geek out anyway. So here we've got a common picture that you'll see a bunch of times today, 3 availability zones. Now at the bottom there, we have Aurora storage. Storage is really what makes Aurora special. So you can see the first thing is that big blue box covers all 3 availability zones. So we have 3 availability zones storage out of the box with Aurora, no questions asked. We have a bunch of yellow boxes. They're the storage nodes. There's normally a lot more than 9 of those things. And we have your application, 2 application nodes running in 2 different AZs. They're talking to 1 read-write node here, and they're talking directly to the storage. And that storage, what are we writing to that? We're writing log records, database log records. So they're the instructions to change a piece of data that a database would normally write. And the storage special part about it is it understands how to turn those log records into database pages. So that means that there's no checkpoints like a traditional database. There's no full page writes, there's no double write buffers, there's no log archival. All those kind of problems that you'd normally hit with traditional database, they don't happen here. You can also see some of my cool color coding there. There's 6 copies of each piece of data written across 6 of those storage nodes. So every time you write once, we get 6 copies across 3 AZs. That comes out the box too. We write those log records, but we read back database pages. So that's because the storage can turn those log records into pages. Right? What happens if one of those pieces of log record maybe gets broken or gets missed? Well, we'll just peer-to-peer repair it from another storage node in a different availability zone maybe. What happens if a whole storage node goes away? Well, again, we'll just peer-to-peer repair that from another one. So this is all happening under the covers, the database engine, and you don't even know that it's happening. We can add another replica. Here, it's this read-only one. It's reading from the same storage. So there's no consistency lag between these 2 things. It's the same storage. We're doing async invalidation and update between those 2 head nodes. So when we run a transaction on the read-write node, then the read-only node finds out about it within just a few milliseconds. We can add up to 15 of these replicas in different AZs, or the same AZ if you want to. Again, this is not disruptive. We're not having to reboot any of the cluster, any of the other replicas in order to do this. We can add or remove them as we like. These replicas can be different sizes. They can be different types of instances. Here we have an R8G, which is a Graviton. We have an R7i, which is an Intel. We have a DV.serverless, which we'll talk about some more later as well. The storage expands up to 256 terabytes automatically. You're not provisioning this space. You're not provisioning performance here. This is completely elastic and automatic. When something goes wrong, maybe we lose a whole availability zone of those head nodes, right? We're able to automatically promote one of those replicas to be the read-write node. And your application will check into Route 53, the DNS server there, we'll change the endpoint, and we'll start to talk down to the read-write node. So if you want to have even faster failover than that, normally that's about 30 seconds because you're waiting for the DNS. You can use the advanced rapid drivers for JDBC, ODBC, Node.js, a whole bunch of other ones. And they'll be able to changeover within just a few seconds there. So it's up to 66% faster. That's the whirlwind tour of Aurora architecture. I'll test you later, see if you got it, all right? One of those things that allows us to do is to go multi-region. So this is the same picture on the left, and on the right we have another region, global database, this is called. So when we add another region, the most basic thing we can do here is we can just asynchronously replicate the storage. And if we look carefully, those orange arrows are coming through the replication server going over to the replication agent, which are things that I manage, not what you manage. They're coming from the storage, not coming from your head node. Your head node's not involved. So your application doesn't know that global database is happening. It doesn't have to make any changes. We replicate over. So when you write, those log records go up, they go through the replication server and agent and into the storage for the other side. Now we can make some replicas on the other side as well in region B. They'll be read-only because this is a single writer system, and they'll be able to see that same data within whatever your RPO lag is there. So it's typically less than a second. It depends on your choice of the two regions. You can have up to 10 of these regions, sorry, if you like. You can put your application running inside that other region too. This is a really cool pattern for doing low latency region local reads, so you don't have to worry about the cross-region latency. So with global database comes the question of how do I know which region I want to talk to? Where is the writer? That's where global endpoint comes in. So this is a DNS name that points to the region that is the writer at this point in time. Right now it's region A. So then what happens if region A has a problem? Well, you're going to issue a failover operation. You're going to tell me, Tim, you need to fail over and make region B be the primary region, please. So I'll promote one of those instances to be the writer node. You can see there's that -- allow data loss flag down there in the bottom right corner. That's reminding us that because this was asynchronous replication, there might be a little bit of data inside that asynchronous replication window that might be lost when we do a forced failover. When we've done the failover, we've promoted that one to be the writer. We'll also update the DNS name for that global endpoint using the Route 53 data plane API. So that's really reliable, really quick, much better than you could do with your own DNS. So that was a failover operation. That's when something's broken. So global database switchover happens when something's not broken. We have two regions, they're both healthy, and we just want to move the writer maybe from region A to region B in this case. Maybe because you want to follow the sun with your operations. So we've recently announced some improvements here. We've gone down from about 5 minutes of RTO here to about 30 seconds. So I really want to explain to you how it works. You can see down the bottom left corner, there's those coloured squares. That's those log records, right? And they are in a time sequence. This one was written before this one, before this one. And we say, I want to do a switchover at this point in time. So I'm going to write a special one of these log records into that log stream. That's my little star there. And that's going to flow through the normal replication machinery there. And when it pops out in the second region is going to see that. It's going to interpret that as switchover now. So we can use this log-based architecture of Aurora to get really fast switchovers. We can get RPO of 0, because we're not losing any data, and an RTO of about 30 seconds. If you'd like to learn some more about this, then there's DAT441 you can watch the recording of, because it happened yesterday. All right. So local write forwarding. This picture here, we can see we've got two availability zones, we've got two application nodes and two replicas. What I'd really like to do is be able to write from my secondary availability zone 2. But I've got a single writer system, so if I try and send that write to the read-only node, it's not going to work. So I can turn on local write forwarding. Now this does not make us an active system. What it does is when we send a write down from availability zone 2, we'll forward the write over to the other side. It'll execute the write exactly as it normally would, and then the results will be pulled back again. So here's a bit of an experiment I did. One of the questions comes is, well, how do I know about consistency? Because this was asynchronous replication, right? So we got 3 different consistency modes, visibility modes. The default one is session. My test here does an update inside a session, and then it selects the thing that I just updated, and then it selects the thing again that I just updated, right? So in the session visibility mode, we can see I did the update. It took a few milliseconds because it had to go across to the other side. And then when I did the first select, I had to wait for it to come back again. In the eventual consistency mode, this is like the no seatbelts mode, where we don't wait to read our own writes at all. So we did the update, it took whatever time it took, and then when we did the select, that came back really quickly because we didn't wait for anything that was happening on the other side, right? Maybe we did not read our own writes in this case. Maybe that's a bit confusing for your application, so you have to be careful. The other option, the extreme other end, is global consistency, right? Where you always wait for everything that's happening in the whole cluster. So you can see that the first update took quite a while because we had to wait for things to come back, and then the selects, they all took the same amount of time too. So write forwarding is useful, but you've got to watch out for your consistency model. So we can extend that. We can talk about global write forwarding. So it's a similar picture, but we've got 2 regions now instead of 2 availability zones. We've got the same problem. Read-only node tries to write, can't write. I want to turn on global write forwarding. Same thing happens. I'll forward the query over to the writer region, I'll execute it, and I'll pull it back again. We have the same consistency modes, the same considerations that you need to be aware of. Obviously, the latency numbers will be a bit different because we're talking about cross-region. So that's global write forwarding. Again, it's available on most modern engine versions. Right, so I'm going to dig into the storage a little bit more to explain how it works. So here we're looking at an Aurora storage node inside what's happening. And we've got our read-write node, and it runs a little storage daemon. This is basically the driver that lets our engine talk to our storage here. Okay, so we're going to write this log record called A. It's going to come into the storage node. Remember, this is 1 storage node out of 6, so this is actually happening 6 times. Comes into this incoming queue. That's in memory, so we drain it from the incoming queue to the hot log. That goes to disk. Now we can acknowledge it because it's safe on the disk. Then we do it again. Here comes write C, goes into the incoming queue, goes down to the hot log, acknowledge. It's all good. Now, if your alphabet's any good like mine, you'll notice that B is missing in the middle there, and maybe it was just delayed in transit or something. So we can just go and peer-to-peer fetch it from some other storage node. Here comes B. So now we have ABC all in an order, no gaps. We can move things over to the update queue, and we can then turn these log records into pages again. We call that coalescing. This is all happening really quickly inside the storage. So then when we need to do a read request, we've got it ready, so your read latency is not impacted. This storage node is also continuously dropping all of those log records and database pages into S3. This is a continuous backup, so you can do point-in-time restored any point in the last 35 days in your retention window. Now, in IO Optimize, we'll talk about this more. This is a configuration option. We changed some of this to increase throughput for IO-heavy applications. What happens is we change that storage driver over on the left-hand side there, so it's batching more aggressively. It's really good for IO-heavy applications. And with new modern engine versions, we can turn this up to the next level. We changed that incoming queue to be a durable queue. So now when I try and write log record D, it comes in, it's going to be durably queued directly in that box. We don't have to wait for it to drop down to the hot log, so we can acknowledge it directly. This means that your latency goes down because I have to do less work, your jitter goes down, and performance improves. We'll see some results for this in a minute, all right? Okay, so Aurora Postgres is fully Postgres compatible, so we also always take in Postgres updates from upstream. So I want to just talk through some of the laundry list of what we've got here, and this is a very long list. Lots of things are missing, so I apologize if the thing you're looking for is not here. We support up to Postgres version 17.6, I only just did that last week. We support the R8GD instance type with a local disk. We'll talk some more about that today. We've got a bunch of performance improvements from upstream, correlated subquery cache, adaptive joins, tons of stuff. Shared plan cache. So this is when we've got multiple Postgres processes running. They each have to plan their queries, and they can look in a shared cache. It saves a bunch of memory. We improve read availability for large instances and large replicas. They can boot up faster. We do FIPS 140-3 security encryption across the board now. Lots of extensions have been updated, PG Vector being the most interesting one for some people, and up to 256 terabytes of volume size. Like I said, a whole bunch of other things in there. I just want to focus in on a few of them today. So let's look at Aurora Postgres performance throughput just over different instance generations. So this is a sysbench read-only test. Basically, it's a CPU test. It's all in memory. The purple line, we've got an R524X large, so that's the biggest instance we had 10 years ago at the birth of Aurora. And then the blue line, we have an R7i48X large. So that's twice as big, 2 generations newer, still Intel. The y-axis is queries per second, so higher is better. We can see that that's a 2.1 times improvement in performance. This is CPU-bound performance, just by doing a couple of upgrades of your underlying instance right there. It's pretty straightforward. So then if we add in the R8G, so this is the Graviton version, next generation one, current one now, 48x large, same size. Again, we could get 2.7 times improvement against the baseline there. So that's better than linear scaling. If you did nothing else other than just follow the normal scaling rules that we were giving you, you get 2.7 times over 10 years. That's pretty impressive, I think. So first new feature I want to talk about today is Aurora Postgres dynamic data masking. So this is for organizations using Aurora that need to protect sensitive data. So maybe you've got an example here, you've got account numbers, you've got account holder names, PII kind of stuff. You've got an account balance. Maybe you want to give that to an analyst, but they don't need the exact balance, they just need some rounded version of the balance. That's what dynamic data masking is for. So what we want to get to is we can mask things out, maybe make them X's or something. We can apply some different functions to do some rounding, something like that. Right? That's what dynamic data masking lets you do, but it lets you have the full expressive power of SQL. So you can still do joins, you can still do use all your indexes, all those things. So let's see how it works a little bit. So it's implemented in Aurora in this new PG column mask extension, where we define a policy for masking for, in this case, it's called fully masked account data for my example. We're going to apply this to the accounts table. And then this is a list of the columns that we're going to be masking. So this customer ID one, for example, we're going to mask and turn it into X's. And this account balance one, we're going to apply this round function. That's how we want to do masking. We're going to apply it to all of the roles that are in this list. This list has only got one role called analyst. And it's got a weight of 50. This weight is used when we have overlapping policies, so we know how to apply them. All right? So this is pretty useful, I think, already, but I want to talk about how it's actually implemented because I think that's interesting. So we have this select query, right? How does this actually work? Well, inside Postgres, we have this pipeline. We parse the query, analyze, rewrite, and plan, etc. So this actually plugs in, DDM plugs in the query rewrite layer. We rewrite the query to fetch masked results. We don't mask the fetched results, if you like. And that's how we can get by and have really good performance and make your indexes still work and things like that. That's pretty important. You don't have to believe me. You can see the action of this in the describe output here. You can see the mask function there being applied to that column. So now for MySQL, Aurora MySQL, again, we track upstream. Same story with the laundry list here. I apologize if your favorite feature's not here. The list is just too long. So we released 3.11 just a couple of weeks ago. That gives you MySQL 8.0.43 compatibility. We also released a 3.10.0 long-term support version. That gives us an in-memory relay log cache. That's up to 40% log replication throughput if you're using bin log replication. That's pretty awesome. We have those advanced wrapper drivers that we talked about. So now they support ODBC as well for MySQL. 256 terabyte volume support, and one that's pretty neat for me, global database secondary readers. So when something happens in your global database, those readers can now stay up and serve you reads for longer. So that increases your read availability when you have a global issue. So now Aurora Serverless. So this is the instance type that I'd like most of you to consider for your workloads. It makes managing your fleets easier because you don't have to worry about instance sizes. This is what we used to call Aurora Serverless V2. V1 went end of life, so now we just called it Aurora Serverless. Naming is hard, I'm sorry. Just bear with me with the names, okay? So what is Aurora Serverless? So it's an elastic instance type. You can think about it as just an instance type like a 4x large or something, except you can plug in and plug out CPU and memory, and we do it for you automatically as the system needs, right? Every time we do this, there's no impact. It's not like we're rebooting your engine or anything. We're doing this every second. We're scaling up and down the memory, CPU, and network for this instance. We measure this in units of an ACU, Aurora Capacity Unit, which represents 2 gigs of RAM and the associated memory, CPU, and network that goes along with it. So here on the right, we have a Lambda, and it's talking to a small serverless instance. And then another Lambda comes along and it wants to talk to that instance, and it sends it tons of queries, so it's too big, so we need to scale it up a little bit, so we will. Then a big analytics job maybe comes along, and so we need to scale it up some more. And so we're scaling up and down, and we price this per second. So as soon as we scale back down again, you're no longer paying for the things that we scaled up, right? So this cost curve, we'll see some more of this in a second. Concrete example. So we start off with an example with 4 ACUs, right? Aurora Capacity Units. We are watching for changes in these triggers, CPU, memory, network, and I/O. We also have this bucket of credits off to the side. This is how the scaling mechanism works. So this scaling bucket is being filled up periodically. So as it fills up, it means that if you need to scale now, you've got this many credits with which you can scale up to your max ACU limit that you've set. So now I do need to scale. I've triggered something, maybe I want to use some more memory. So I consume some of these credits out of the bucket. I consume 4 and then I consume some more. So now my instance has scaled up to 12. That's really fast. It's done this in less than a second. But my scaling credits have reduced, so they'll refill again later. So what we've done just recently is we've enhanced the responsiveness of this, so we've given you faster scaling. So the triggers respond in less than a second now, our bucket size is bigger to begin with, and it refills faster too. So what I want to talk about is some performance examples with this in a second. The other thing we've done with Aurora Serverless recently is introduced platform version 3. So this gives you up to 30% improved performance. It's available for all new clusters. So all you have to do is just restore from a backup or a clone or make a new cluster, you'll get this. It's not even an option that you need to select anymore. So this will give you up to 30% improved performance. So let's look at both of these two things combined. First test here, this is just for faster scaling. So this is platform version 2. Yellow one is fast scaling, red one is not fast scaling. Okay, this is a sysbench read. So we're pushing pretty hard, goes up to 210 or so ACUs. What we first notice is that yellow curve is a lot steeper. We're scaling up a lot faster than the red curve is. Then because we scaled up faster, that peak performance at the top runs for longer, so we can get your workload done more quickly for longer time, 3.6 times longer. And then we scaled down at 40% faster too. So if you integrate all of that, then towards the end, you'll notice that's used 9% fewer ACU hours. They're the things you pay for, right? So you're paying 9% less for this particular test. That's great. So that's platform version 2 faster scaling. So now we turn on this platform version 3, the new thing here. We stick with faster scaling. So similar test, it's just a little bit heavier so we can push even harder. And we look at the purple line there. That's platform version 3 with faster scaling. And the yellow one's platform version 2. The first thing we notice is the purple one runs for 20% less time because it's going faster, right? So it doesn't need to run for as long to get the same job done. And then at the end of it, because it's scaled down, we use 20% fewer ACU hours. So that's 20% less bill that we'd have to pay by combining these two features, faster scaling, platform version 3. All you have to do is make a new cluster. You'll get both of these with no extra effort. Okay. So now another one. Let's talk about one of Aurora's newest innovations. It was announced only yesterday and pre-announced. Aurora Create with Express configuration. So how often do you, people in here, create database clusters? My guess is that this hand-drawn diagram, which is of course completely accurate, represents this population of people in here. So over on the right-hand side, there's the enterprising mindset people who don't create database clusters very often, like basically never. Then there's the guys in the middle who create maybe every week or something, but then there's this population that wants to create things like almost every second. Maybe this is the CI/CD kind of people, right? You want to do things really agile, really quickly. I want to address that orange part there. So that's where Create with Express configuration comes in. So this was pre-announced yesterday, coming soon. So for Aurora Postgres, what this does is we can create a DB cluster in seconds. And that lets you open your mind to now using it in those CI/CD pipelines. You can use it from your agentic AI applications. You create a new database for every single interaction with that, if you like. So we can see here a few things. So these fields we can set. We create in a few seconds. We've got a flexible configuration there. So this is serverless. We start off with 16 ACUs, if you like. This is an editable field. We can change the name. We can only select a couple of Postgres versions at the moment. But you can see that right-hand column, modifiable post-creation. So it's yes for most of those things. So even if you don't like the defaults that are here, as soon as the cluster's created, you can change it if you like as well. So this one starts off with 16 ACUs. That's good for a lot of people. But if you want a provision system, that's fine. Just bring up your serverless one and switch it over. We can just fail over like we talked about before. Then it's secure by default. So you get encryption turned on. You get IAM turned on, all by default. And it supports almost all the Aurora features. This is a regular Aurora DB cluster that we're making. It's not something special. So you could do global database, I talked about before, Zero-ETL, all the other features we talked about before. Backups work the same. It's all the same. So one of the new bits that I want to talk about a little bit more is this no VPC thing down in the bottom there. So that's pretty interesting. So without a VPC, you need a way to get to your database instance. You probably don't want to put your database instance on the internet. That's normally not good practice, right? So it's Aurora Internet Access Gateway is this new component we've built which allows us to deal with this. This is a highly available endpoint that gives us access into your Aurora cluster. It's Postgres wire protocol compatible. It's not a big heavyweight proxy, so it's not giving you tons of latency to worry about. So that means you can access your DB cluster from anywhere, your laptop anywhere. You don't have to worry about VPNs and VPCs and things like that. Really reduces the friction for you and your developers to do whatever they need to do. So this also integrates with Amazon IAM, and it integrates with AWS Shield, so we can talk about the features that it provides, like fraud protection and other ways to safeguard your data. Right, so that's Internet Access Gateway, comes by default turned on when we do express configuration creates. This is not an agentic AI talk. Laughter, good work. But I have to talk about some of the cool things we've done here. If you would like to see an agentic AI talk, there is another one down the bottom there. If you want to listen to me tomorrow, you can hear about that. But there's two really interesting things that I want to talk about here for Aurora, just in the very last minute. So a critical component of agentic AI is a loop, right? So you need memory for this thing to work. Well, I'm a database. I figure that Aurora's pretty good at being memory. So how can we do it? We want to remember something like its favorite color is blue, something that we want to do. So you can use any one of these open source frameworks. We partner with a bunch of people already, like Vercel or Letter. So here's an example of doing it with Letter. So it's only like 3 lines here, right? We've created a DB cluster with that express configuration we just talked about. Takes us a few seconds. Then we go in there, we enable the PG vector extension just because we want to do some vector embeddings for our LLM maybe. We don't have to do that. And then we can turn on, tell Letter to start its Docker container and just point it at that Postgres endpoint. We're done. Now you're using Aurora Postgres for agentic AI memory. Now, this is the Letter example. There's a bunch of blog posts or other things, so I encourage you to go and have a read off for the other frameworks of your choice, LangChain and all kinds of ones. Right. The other thing is MCP servers. This is Model Context Protocol Server. So this is the glue that lets an agent find the tools that it needs to talk to and talk to them. So AWS open sourced a whole bunch of these MCP servers for all its databases a little while ago. What this allows us to do is run natural language queries that understand the schema of what's going on inside an Aurora database and turn your natural language queries into SQL queries. So this is super useful if you're new to a database, you're just spelunking around, trying to find your way around, or maybe if you're a power user, this will make you much more effective. Okay, that's it for generative AI. Patching and upgrades may be a bit more close to a lot of people's hearts. So hopefully I've convinced you and you've already got tons of Aurora clusters going already, and now you're worrying about how to upgrade and patch them, keep them secure and up to date, right? So Aurora's always given us a managed experience here, right? So I have a console screenshot here. We have a pending maintenance action. It's telling us I need to apply some system update right now. And this is a managed flow. You would just click go and it would go and do it for you. What do we do differently now? Well, OS patches, they happen in a rolling fashion now, so that if you have multiple nodes in a cluster, we'll just roll through them. That increases your availability. That's great. We have a maintenance window. You've always been able to set that maintenance window. That lets you set the day of the week in which you want to take maintenance on this particular instance. We give notifications, so if it's happening or not, this pops up in AWS Health. And you can opt into this being automated or not. Some people opt out of it because you want to control it from your own Terraform or something. That's completely fine too. So this is one DB cluster. I think it's pretty under control. Now, when you've got a fleet of clusters, I've convinced you all, you love Aurora, you've got tons of them. You've maybe got some dev ones, some QA ones, and some prod ones, something that you want to sequence the upgrades for, right? If you wanted to do this yourself today, maybe we want the dev ones to happen on Monday, and then we want the QA ones to happen a couple of days later, so we have some bake time just in case something goes wrong. The prod ones we want to happen on Saturday so that we can do it out of business hours, right? There's not very much time between Monday and Wednesday, not very much reaction time. There's also, I don't know what's happening inside your databases. I don't know which ones are your dev ones and your QA ones. So I might announce maintenance on Tuesday. And if you have a setup like this, then your QA ones will be upgraded before your dev ones, which is probably not what you want to happen. So what we did was we've announced this AWS Organizations Upgrade Rollout Policy just last week to tackle exactly this problem. So here we have our same 3 environments. And what we've done is we want to break them into 3 waves. First wave, second wave, and the last wave, which is really what you were trying to express to me anyway, I think. So what's going to happen is, first we'll notify you, give you a maintenance notification, just like we did before. And then we'll wait for the maintenance window for all the resources in that first wave to come along. And then we'll upgrade all of those instances in the first wave. And then we'll bake for a while, a lot longer than we would have baked before, so you've got some time to react. And then we'll wait for the maintenance window to come up for the resources in the second one, and then we'll upgrade them. Guess what? When we wait some longer time, and we do it for the last wave as well. So we're not actually blocking if something's going wrong from one wave to the next, but we're giving you enough time so that you can just opt out. Again, you can turn the tag off or turn off AMVU if you'd like to. We're upgrading these things in sequence, so it doesn't matter which day of the week I release an update. It's going to happen in sequence for you. All right. So how do you do this? How do you onboard with this? You have to enable AWS organizations if you haven't already. You have to put your accounts into the organization. You have to do the normal things you would do, like enable automatic minor version upgrades, check a maintenance window that says what you want it to say. Now the interesting part. We have to set a policy. So on the left, we've got the console version. On the right, we have the JSON version of the same thing. And what this is telling us is allowing us to associate a tag. You're probably already using tags on your resources. Here we're going to make a tag called env, not a special word. You can call it whatever you like. And we're saying that, okay, every resource with a tag called env that's got the value of prod, for example, I want to put it in the last wave. And if there is a tag that I don't recognize or no tag at all, that's going to get the default, which is the second wave in this case, right? So you don't have to do tags at all. If that's not what you're interested in, you can just accept the defaults, that's fine. And everything will be upgraded at once. All right. So then once you've created that policy, we can attach it to either your entire organization, the root, or to individual accounts in your organization, so you can be selective here. And then when an upgrade actually tries to roll around, you'll see this in the normal way. You'll see in your pending maintenance actions, up in the top left there, now it says this is going to happen in the second wave. And then you'll also see this in AWS Health. Same thing there, you'll get a health notification with in this case, the second wave. So I think that'll really help. So give that a try. That's the organization's upgrade rollout policy. Okay, blue-green deployments. So all of these techniques are fantastic that I've just talked about if you're doing compatible upgrades that we can roll through. But when a major version upgrade comes along from open source, these are generally incompatible by definition from open source. So we can't do them in place without taking a bunch of downtime. Probably you don't want to do that. So blue-green deployment, what is it? So here we have our production environment up the top there, a couple of Aurora nodes, some shared storage, your application's talking to it through an endpoint. When we want to create a blue-green deployment, so we're going to, in one click, create a complete copy of your production environment. We're going to make all the nodes be the same. We're going to sync up all the data using logical replication and keep it in sync. As long as you keep this blue-green thing running, any new writes that are coming into the blue, they'll be pushed down into the green already, right? Once that's done, then you can upgrade that green environment. You can test it with your test application. You can do whatever you like. You can spend an hour here. You can spend a week in this situation. Doesn't matter. When you're happy that the upgrade's done what you want it to do, then you can do what's called a blue-green switchover through the CLI or the console. And we take care of renaming all of your AWS resources so that you're not left with a bit of a mess afterwards. We make sure that we drain the logical replication first, so you're not going to lose out on any data. We're going to switch the endpoint around, and your production cluster just keeps on talking to that endpoint. And now it's talking to what used to be called the green environment. We have the old blue environment is still left behind there, so you have a look-back plan again if something goes wrong. If this times out for some reason, normally the switchover is less than a minute, but if this times out for some reason, then we'll automatically undo it and go back to the original blue environment. Again, you don't have to deal with anything. So that's Aurora blue-green. It's a great way to increase your availability when you're doing these major version upgrades. I'd much rather you do the version upgrades rather than stay on an old version. Don't think anybody wants that. Okay. And it's useful not just for version upgrades too. It's useful for schema changes, static parameter changes, maintenance updates, anything else that you think is a bit too risky to do in place and you want some blue-green protection from, you can use a blue-green deployment. Now, the interesting thing that we just talked about with blue-green just last week is support for global database. So now I've got a 2-region picture here, right? Remember, it could be up to 10 secondary regions, but we have a global database. We're doing that replication, physical replication, and I say, I want a major version upgrade that thing. Well, now I can use blue-green to do that as well. Same idea, I make a green environment, I keep it in sync with logical replication, everything I just explained works the same way. We end up with an RPO of 0, we're not losing any data, and the RTO is about 1 minute, so our switchover time is about 1 minute. So the entire global cluster can do a major version upgrade and be managed that way. It's pretty new, and I encourage you to take a look. Okay, so let's talk about another neat feature that's enabled by the way that Aurora disaggregates its storage. This is Aurora's Zero-ETL, for extract, transform, load. So on the left there, we have an Aurora Postgres, and we have a Redshift, and we want to get our data from a Postgres into a Redshift, for example. We want to do this in really low latency, and I don't want to manage, well, I don't want you to have to manage the ETL pipeline that goes along with it. Because that's hard work, that's brittle, that can be expensive, it can be time-consuming. So we can add a Zero-ETL integration. This is a CLI that you can run. What that does is it tells me to make a pipeline between the Aurora cluster and the Redshift cluster. Easy as that. And we'll have a 5 to 10 second replication lag. So once you've written something into the Postgres side, it'll pop up in the Redshift side within 5 to 10 seconds. That's a really good turnaround time for an ETL pipeline. So if you were to do this yourself, you'd have to worry about data seeding. How do you start this thing off from empty? You'd have to worry about how to do this with, how to do maintenance of this. We'd handle all that stuff for you with Zero-ETL. The picture gets a bit more interesting because we can do multiple Auroras, maybe even different ones, MySQLs and Postgres, into the same Redshift that you might already have in that same data lake. We can add even more of them. We can also go from Aurora MySQL into SageMaker as well. It uses the same technology. So I think this is pretty cool, but I think it's even better is how it works inside. So that's what I want to get into, is how it works underneath. So here I'm talking about a MySQL one, just because that's the one I like to talk about better. And we talked before about how Aurora understands the physical transaction log of what's going on. But in order to do CDC streaming, change data capture streaming, we need to have a logical log, not a physical log, right? So that's not the thing that Aurora traditionally knew how to deal with. So we have to capture that CDC log. We also have to be able to seed this data to begin with. It's no good having a change log if we have no basis to base the change on, right? So we have to seed it. So firstly, we can start off at the storage layer. We can do parallel direct export. This is where all of those individual storage nodes export directly into the Redshift storage in this case to create a seed. So your head node's not involved in this. It happens really quickly and it doesn't impact performance on your head node at all. Once we've done that seed, then we can use what we call enhanced bin log. So this is a bin log for MySQL, or the WAL for Postgres, still works the same way. But this is where we put knowledge of the format of that log, that logical replication log, into the storage, so we understand how it works. So then the storage nodes understand enhanced bin log. We spin up these CDC streaming servers. They read that CDC log from the storage, not from your head node. So by turning this on in your head node, you're not hurting your performance there, which is what commonly happens with MySQL-based systems. That CDC streaming fleet's going to apply filters there. It's going to throw away the tables that you don't want. It's going to do all the modifications, and it's going to push that data down into Redshift. So there's no arrows between MySQL head node and Redshift. It's all going through the storage, so you're not feeling any of that performance impact. I think that's pretty neat. So let's talk about Aurora storage types for a minute. We talked about IO optimized before. We'll go into a little bit more detail. So here's Aurora standard. This is what you get if you don't choose anything. Have the same picture before, and we're going to talk about the life of a few IOs and how much it might cost. So application, it's going to do a select. So this is read only, right? Inside your head node, you've got a cache. And we get a hit on that cache, so it's not going to cost you anything other than a few milliseconds of running the instance, right? No I/O. Or it's going to miss the cache and it's going to go to storage and it's going to read a database page, which will be 8K or 16K, depends on your database engine, and it's going to cost you a fraction of a cent. So what's going to happen then when we do a write? Remember, we're writing these log records. They can be varying sizes. They can be batched together in different ways. When we do a write, up to 4 kilobytes, that'll cost you that same fraction of a penny, right? The tricky part comes when we do different types of writes. We might batch them together in different ways, and that might not be batched into one I/O. It might be batched into up to 4 I/Os, right? Because they're 8 or 16 kilobytes in size. So this is an unpredictable pricing model, which sometimes it works out pretty well, and sometimes we don't like the unpredictability. So we wanted to give you an option to say, how can I make this more predictable? This is where Aurora I/O Optimized came in last year. So this is a pricing choice. You can choose this whenever you create a cluster or at any time afterwards. You can switch it online once a month, no problem there. What this does is it changes the way that both the performance of the system, the way that it works, and the way that it's built. So it's a cluster level configuration, not an instance one, because there's some storage side changes too, and these are storage is shared. So what I encourage you to do is to look at the I/O proportion of your Aurora bill if you're already using Aurora. And if that I/O proportion is more than 25%, look at I/O Optimized. It will probably actually save you money. I'm not trying to sell you something that's not useful. I think it'll actually save you money and give you better performance and give you predictability. And even if your I/O proportion is smaller than 25%, give it a look. You might like the performance too. Okay? So this is available in all modern engine versions in the last 18 months or so. And it's also compatible with the newly announced database savings plans, if you watched the keynote this morning. So how does this work? So in terms of money, on the left we have Aurora Standard, which we talked about. So this is the normal AWS method. You pay exactly for what you use. So you're paying for compute, paying for storage in gigabyte months, and you're paying for I/O. At some rate, depends which region you're in. Then in the I/O Optimized SKU, if you've chosen that, then you'll pay for compute at some slight premium, you'll pay for storage at some premium, and you'll pay nothing for I/Os, zero cost. So you might look at those percentage numbers there and become a little bit worried, but I want you to just remember back and say, if your proportion of I/O is about 25% or more, this will probably actually save you money. So let's look at this example again. It's very easy to explain because all the numbers are zeros. Doesn't matter if I cache hit or miss, doesn't matter how I batch up the writes, it's just zero, right? Very easy to understand, very predictable. Cool, so let's look at not just the pricing part of I/O Optimized, but what it's going to do to performance. So this is throughput. This is a HammerDB test on a 16x large, not the biggest box, but it's a pretty big box. It's pushing pretty hard. The y-axis is NOPM. This is the metric for this benchmark. Higher is better. And we start off with an R5, which is that older instance type. And it's the version 12 APG. So this is extended support version, old baseline. Right? It looks okay. So then we turn on an R6i, 16x large, version 14. Not much difference in the Postgres version there. And we turned on I/O Optimized. We get a 1.9x improvement, basically just by turning on I/O Optimized and going up one generation. R6i is still not very new. We turn on an R7i, version 16 Postgres, another 10% just by doing an upgrade. We go to version 17, the most recent one, same instance. We get another 10%. So all you did was upgrade Postgres major version that time. Probably used Blue-Green to do it, right? So that's even better. That's good for throughput. 2.3 times overall improvement in throughput there, just by turning on I/O Optimized, probably reducing your bill if you're working the system this hard, and upgrading a few Postgres versions. Okay, so now let's look at the latency of a similar test. This is actually what we built I/O Optimized for. The throughput ones were just bonus points. This is where the money is, right? So this is sysbench write only. This is a latency on the y-axis, so lower is better. The blue line is the R5 24x large, version 16 Postgres. We can see how it's getting saturated towards the right-hand side there. The latency's kicking up. We don't like that. Then we got the pink line. That's an R8G 48x large, version 17 with IO optimized. You see how that line's almost flat. That's really what we want from a latency graph. So over on the low end, we've got a 3 times improvement in latency. I would be very happy with that. But on the high end, we've even better. We've got a 6.4 times improvement in latency. That's the thread count along the bottom there. So the harder you push, the better this gets. So IO optimized for latency. Now, if we turn this back into throughput, we have the same test again. We can look at it there. So this turns into a 5 times improvement in throughput in those same 2 baselines, just by turning on IO optimized and going to R8G. So give IO optimized a shot today. And if you don't like it, that's fine. You can just switch it straight back off again. It's all on lines, no failovers or anything like that. So that was all about writes. Now we just want to talk about reads too. I didn't forget about that. So one part of the puzzle is temporary objects. So when your Postgres is doing something like a really big index rebuild or a really big sort, it might run out of memory and it needs to spill to disk. And in a normal system, that disk is an EBS disk, so we have some performance considerations there. So if you choose a D instance, like an R8GD, then you have a local NVMe instance storage device inside your database instance. So then when we spill to disk, we'll spill to that thing instead. Up to 6 times the size of the memory we'll allocate inside there, right? So that means obviously the latency is a lot lower there. We'll improve our performance dramatically for workloads that use those temporary objects. Right? So if we turn on IO optimized though, we reduce that 6 times down to 2 times your memory. Still good, still works the same way, but it's only 2 times the memory. So what's the point? Why did I save all this space over on the left there? That's what I want to talk about. In that space, we put this thing called tiered cache. So if you're on a regular APG and you do a read, you're going to look in your shared buffers in memory first, and if it's there, we'll read it back and we'll be done, no problem, right? If it's not in shared buffers, like it's not now, we'll go to storage. We'll read it back into the shared buffers, we'll give it to the engine, we're happy, okay? So when we turn on optimized reads with one of those D instances, in that space, we're going to allocate 4 times the amount of memory that we've got on the disk, and we're going to use it like we use shared buffers. It's a cache now. And we're going to take a little bit of memory to handle some metadata there for us. So now when Postgres needs to read something, we'll check that metadata and see if the thing I want is going to be in the disk cache or not. In this case, it's not. So I'm going to read it from the storage directly into your memory buffer, give it back to the engine like before. So the fact that tiered cache was there did not help or hinder us in this example. But now it's there in the shared buffers. That's good. Eventually, shared buffer is going to get full. We're going to have to evict that data out somewhere. So instead of just throwing it away, we're going to evict it down into the tiered cache. We're going to keep a little piece of metadata up there to remember that we've done this. So now when we go and try and read that data, we're going to check that metadata and see that it is there. So I can just fetch it back from tiered cache. It'll be nice and fast, low latency. Now, if I do an update, I need to invalidate that copy that I have in the tiered cache, right? But I don't want to go and write to it all the time. That would be pretty bad for performance. So all I need to do is really just flip that metadata bit so that I forget the fact that I have that data in the tiered cache. That's what we do. So now when I try and read it, it doesn't matter. We're not going to go and look there. Recently, we added the ability to change the size of the tiered cache versus temporary objects. So if you have a workload coming where I know I'm going to need to spill to disk quite a bit, I can increase the temp space. Then that workload's finished, I can decrease it back again and have a nice big tiered cache. So that's now elastic and dynamic. So R8GD instance, that's a new one there, and that's the same price as an R6GD, so they're exactly the same price. So you're going to get, I think it's 165% improvement of performance versus an R6G. So for the same price, I think you better go and check it out if you're using tiered cache. And if you're not, maybe give it a look. So let's look at some performance examples here. This is a histogram, so we want to be over towards the left and up high as much as we can. It's a latency histogram. So now we've done a sysbench point select and we're doing a uniform distribution. This is a terrible test. It's like really random. It's not like what a normal system would do at all. And this all fits in memory. That's why we've got a really tight spike over on the left-hand side. Latency is good. Now we do a much bigger test, 340 gigs, that does not fit inside a 4x large memory. And so we can see a spike over on the right-hand side where we're reading from Aurora storage. That's 4 times higher latency. So then we're going to increase the size of that test again, and we can see the same kind of pattern, right? We're reading from Aurora storage, and the latency has gone up about 5.5 versus the baseline. So now we turn on tiered cache. We look at that 340 gigabyte one, we look at that yellow spike. That's in that space there, that mid-range latency, a little bit worse than memory, much better than Aurora storage. That's where all your reads are coming from. Notice there's no spike at all in the Aurora storage side in the yellow. That's because it all fits in tiered cache. So only a 1.5 increase in latency versus the memory baseline. So now we go to that really big test, the one that doesn't fit in memory at all, and we can still see there are some purple reads over on the right-hand side, but not very many. So overall, there's only a 3 times deficit in latency versus the memory baseline for something that was 8 times too big to fit in memory. This is a really, really neat approach. But that was a uniform random. So now we're going to look at a Pareto random, something more like what your application probably does. And you can see that it's even better. We have the same set of tests here, tiered cache turned on, and we can see that it's only a 1.4 times latency reduction for that massive test compared to the one that fits in memory for a more reasonable distribution. That's really powerful. Right. So to give you a real use case quickly, this is PG vector benchmark. So it's a big N benchmark, really good recall. And we're comparing an R8GD to an R8G. So that's optimized reads versus not. We can see there that's over a 3.5 times improvement in the number of queries per second that we can get there. So then we can add in the R6GD and compare that, just to compare the R6GD versus the 8GD. Remember, they're the same price. That gives us over a 1.6x improvement in vectors as well. Okay, so that's it for Aurora MySQL and Aurora Postgres. Now we're going to talk about Aurora DSQL for a few minutes. And it's not a deep one like I talked about before. What I'm going to give you is the flavor of the differences between these two engines so you know how to think about them. Okay? So on the left, Aurora Postgres. It's fully Postgres compatible. On the right, we have Aurora DSQL. What's common? So we have storage across 3 availability zones in both of them. We're going to have a query comes in and it's going to write to some query processing thing, a head node I called it before, and it's going to write some log records to this storage. All looks same so far, right? Then we're going to add in a second query that needs to come through, second application. In APG, like I talked about, there's only one writer, so it has to go to the same place. Right? We're going to use implicit or explicit locking to deal with any kind of conflicts that are happening because of that. On the DSQL side, we'll spin up a new query processor. This is active-active. It can do multiple writes here. We're going to use optimistic concurrency control here instead. So you're going to have a bit of a race condition going, and one of them is going to back off and have to fail and retry. Right? If I want to scale out, I can add replicas like I talked about before in Aurora Postgres. Now, each of those replicas has asynchronous application between them, so you have that consistency question we talked about, and it has caching, so you have good performance, and then you might fall out of the cache, depends, like we talked about for optimized reads. If on the DSQL side we do this, we have its own distributed block store for handling reads, and that's going to scale independently. So that means that you don't have any caches inside your head nodes, but you have the ability to push down, what I call optimized reads there, you have push down some query predicates in there so we don't have to be so chatty with the reads. So as we scale up some more, Aurora DSQL will keep on adding query processors, and Aurora Postgres we can do the serverless thing like we talked about before, and that can scale all the way down to 0 after 5 minutes of inactivity, in the same way that DSQL will scale all the way down to 0 once we don't do anything, right? So clearly we can see here that this is an active-passive architecture on the left-hand side with Aurora Postgres with explicit locking, and Aurora DSQL on the right-hand side has an active-active architecture. This is all in one region. Okay, so now we'll talk about, we'll just follow reads and writes, look a little bit deeper. So we have our AZ endpoint, 3 of them because we've got 3 AZs, and a read's going to come through. It goes through the AZ endpoint, going to go to some query processor that we choose. Query processor says, I need to read from these 3 storage servers in order to read the data that this query is interested in. Off he goes, fetches the reads, we're done, no question. Now when I want to do a write, say this query is a write, instead the query processor is going to be spooling up all of the writes that happen as part of this transaction. We're not talking to any of the other stuff until the transaction commits. And then when the transaction commits, I need to talk to these things called adjudicators. Remember that I could have multiple of these write queries going on at the same time. The adjudicator is the component that decides who wins and who loses, right? Now in this case, I've touched a bunch of stuff, so I have to talk to 2 adjudicators because these things are sharded. The adjudicator says, okay, you can commit this one, Tim, that's fine. So then we send those spooled writes to one of the journals. The journals are storing these logs across multiple AZs. And then the journal is going to push whatever updates it needs to the storage shards that are impacted. Not all of them, only the ones that are impacted by the things that we're changing. That's important for scalability as well. Okay, so now the global story, the multi-region story. Just very quickly at the top there, we have Aurora Postgres. At the bottom, we're going to have DSQL. So we have some replicas. We have read-only on the far side. We have asynchronous replication, active, passive. We've talked about this a lot now. That means that when we commit, your commit latency is an in-region construct because the across-region latency is asynchronous. In DSQL, things work a little bit differently. When we commit, we're going to synchronously talk across to the other region. So every time you commit, your commit latency is cross-region latency. That's the fundamental consideration to think about between Aurora DSQL and Aurora Postgres. All right, if you want to learn some more about Aurora DSQL, I encourage you to stop listening to me and listen to some of these other talks there. If you want like chalk talks or breakouts or workshops, we've got lots of things to choose from there. And if you've missed it, there'll be recordings as well. So on that note, I hope this gives you some feeling for how Aurora works internally, what we've been up to for the last year. Now, of course, I'm only doing this because I talk to you and you tell me what you want. So I want you to talk to me again afterwards and tell me what you want for next year. And also tell me in the survey how we can do this better for next time. This is really how we're graded. Thank you very much for your time. See you around.